Hi folks, we're going to start this week's lesson by reviewing the latest operation that we've defined, which is the dot product or scalar product. Okay, so if we have two vectors, say u and v, we defined the dot product in two different ways. We had a geometric definition, we had an algebraic definition. All right, so let's take a look at the geometric definition. So we call it geometric because it relies on the magnitude and the angle, similar to the way we originally defined addition and subtraction of vectors. Okay, so the dot product is defined as magnitude of the first times magnitude of the second times the cosine of the angle between them. All right, so we recall that what was interesting about this operation is that we were taking the product of two vectors, yet our result was a scalar. All right. Now, we saw that there were some nice things about this, that if we brought it down to one dimension, essentially just became regular multiplication. Okay, so that's one reason why we refer to it as a product. Also because in order to calculate it, it involves a series of products. Okay, but then we also saw that there were some nice applications. So for example, it became very easy to tell when two vectors were perpendicular. Okay, because dot product ends up being equal to 0 and cos of theta, which would be 90, is equal to 0. Okay, but that became useful when we also defined this algebraic definition. So we had u dot v was also given by, and we call it algebraic because it involves the coordinates of u and b. So let's say u is equal to x1, y1, z1. Okay, we'll do it in 3D, and v is x2, y2, z2. Then the dot product was given quite easily just in terms of the components, and it was x1, x2 plus y1, y2 plus z1, z2, and we see that again it gives us a scalar quantity. Okay, and where the dot product became specifically useful was when we could combine these two definitions to help us determine the angle between two vectors defined algebraically. Okay, so again, the whole idea is to do as much of the work with vectors, especially in 3D where we're not dependent on the angle. All right, so what we're going to take a look at now, and we'll just, we're not going to prove these, although with the algebraic definition of dot product, these are fairly easy to prove. And we're going to look at a whole bunch of the characteristics of this dot product and then take a look at a couple of examples. Okay, so again, if you look at the notes here, we've got our geometric definition. We have our algebraic definition in 2 and 3D, very similar. And then let's take a look at these properties. So we see that, as we talked about, it's a scalar quantity. You don't get a vector, hence why the dot product is sometimes called the scalar product. Okay, you can easily show that the dot product is commutative, meaning order doesn't matter. Okay, here we get to, one of the important ones, that if two vectors are perpendicular, then their dot product's going to be 0. So this is where if I have two algebraic vectors and I want to know if they're perpendicular to each other, all I have to do is calculate their dot product, and if it's 0, I know that they're perpendicular. Okay, then there's a few other characteristics here, which again, fairly easily provable. So here, imagine you've got u dotted with itself. Well, let's take a look at the example. Well, if two vectors are in the same direction, their angle between them is 0, and cos of 0 is equal to 1. Okay, so if I have a vector dotted with itself, I'm just going to end up with the magnitude of u times the magnitude of u times cosine of 0, which is 1, so hence magnitude of u squared. Okay, and if you take a look at these other two characteristics, you realize that dot product has a lot of the same characteristics as working with algebraic expressions. In particular, it's distributive. If I've got a scalar multiple, it doesn't matter where or how I multiply that scalar multiple, and I can multiply it to the individual vector first and then take the dot product, or I can take the dot product then multiply by the scalar multiple. So in other words, what this is telling us, the commutativity and these two properties here tell us that we can treat these vector expressions with the dot product in a very similar way as we treat just polynomials that we're distributing and simplifying. Okay, so again, just a couple of things. That one of the biggies is that we can use the dot product to find the angle between algebraic vectors, okay, using the two definitions, okay, and proofs are much easier using the algebraic definition than the geometric one. All right, so let's take a look at a couple of examples where we're going to use these properties. Okay, so let's take a look at this first question here. It says if the angle between u and v is 60 degrees, then they want us to calculate this combination of those vectors. Now, one thing I want you to realize is that u and v don't have arrows above them. Okay, we see that they have the hat symbol, which means, even though they didn't specifically say it, that these are unit vectors. Okay, so let's start with the original expression here. 6 times vector u plus vector v. Okay, and I just realized here I should stick with the notation since they are unit vectors. Let's use hat. Okay, and then dotted with vector u minus 2 times vector v. Okay, now what's nice about this is because of those characteristics that we saw, we can treat this as though we were multiplying two binomials. All right, so let's do this here. And again, I'm going to use the notation that if I'm not just going to write a multiplication any old way, I have to use this dot symbol. Okay, because I think I suggested last time that there's going to be a second type of product between vectors. Okay, so here we have 6 times u dot u. Okay, now let's go to that one there. That means we have minus 12. Remember, the order in which we multiply these numbers is not important. Okay, so I'll do the 6 times negative 2, negative 12, and here u dot v. All right, let's do the insides here. We have plus v dot u. And then lastly, we have minus 2v dot v. All right. So this is where now I've applied the distributive property to these vectors. This is where I'm now going to use some of these other properties. So let's remind ourselves that a vector dotted with itself is just the magnitude squared. All right. And let's remind ourselves that the dot product is commutative. Okay. So here, u dot u is just the same as the magnitude of u squared. Okay. U dot v and v dot u, these are equal to each other. Okay, so we can treat these two as like terms. So negative 12 plus 1, negative 11 u dot v. And then finally, similar to this one here, v dot v is magnitude of v squared. Okay, so let's keep going. Hey, remember we said, what does the hat represent? The hat represents unit vectors. So the magnitude of u is just 1. So 1 squared is 1. So here I have 6. Okay, minus 11. Well, wait a minute, u dot v. I know the magnitudes of the vectors, and I know the angle between them. I can apply my geometric definition to this dot product. We know that u dot v is going to be equal to the magnitude of u times the magnitude of v times the cosine of the angle between them, which we're told is 60 degrees. And then here again, magnitude of v is 1 squared, still 1, so minus 2. All right, so let's keep going. 6 minus 2 is 4, minus 11 times, well, these two magnitudes are both equal to 1, and cosine of 60. Okay, we can use our calculator, or let's just do cosine of 60. Okay, 1, 2, root 3. Adjacent over hypotenuse is just 1/2. So here we have, I'll write this as 8 over 2 minus 11 over 2. So this is just negative 3 over 2. Sorry about that. All right, and there you go. And you see that what this essentially was just this sequence of applying the different properties of the dot product. Okay, here applying the distributivity. applying the fact that a vector dotted with itself is just the magnitude squared, using the fact that this is commutative so that these two terms were like terms, and then at this point here, using the geometric definition of the dot product, okay, and knowing all the information involved in finding that dot product, I was able to simplify the expression. Okay, so this is essentially the type, but it's almost like grade 9 algebra where you were learning to work with polynomial expressions, except here we're working with these vector expressions whose components have very similar characteristics. All right, so let's do a similar one, but we'll see that this one here has a bit of a twist as we get to the end. Okay, so again, makes life a little easier here that we know that, again, these are all unit vectors. All right, but let's start by distributing. Okay, because the last thing I want to do is actually, so notice what I'm doing here is I'm not calculating the value of the vector in the bracket, or this one here, as I'm using the distributivity to write it in terms of simpler products. Okay, so here that's going to be 2u dot v. All right, then plus 6u dot u. Okay, then this one here, minus 5v dot u. And then lastly, minus 15. Sorry, this one here, I just realized the minus 5 was v dot v. Sorry about that. Okay, here, v and v. And then lastly here, negative 15 v dot u. All right, so similar to before, we've got this term and that term, which are actually like terms because u dot v and v dot u are equal to each other. Okay, so that's going to be 2 minus 15, negative 13 u dot v. Okay, this is just going to be 6 times magnitude of u squared minus 5 times magnitude of v squared. Okay, and as before, let's calculate. We might as well do it in the same step. I can again use the geometric definition. I might say I don't have the angle between the vectors, but I also don't have any algebraic vectors given. So I think I'm going to go the route of seeing if I can do something with the geometric definition, okay? Because I do know the magnitudes. Okay, so this is going to be just 1, so plus 6 minus 5, so plus 1. Okay, I can keep going because, as I said, I know these magnitudes. So what I'm left with is negative 13 cos theta plus 1. And this is where I do run into a bit of a problem, because in the previous example, I was just given the angle between them outright. Okay, I'm not given that information here, but I am given this extra piece of info. So presumably, well, hopefully this is going to be helpful. So what they tell us is that the magnitude of u plus v is equal to root 3. Well, let's see if we can use a diagram to help us out. Okay, so I've got these two vectors, u and v, that are unit vectors, okay, and they give me the sum between these vectors. So let's add these two vectors. So say that's u and that's v. Let's add them together. That's also u, and there you go. Here's u plus v. But I know that u plus v's magnitude has to be equal to root 3. I know that the magnitude of this vector is 1 because it's a unit vector. The magnitude of this vector is 1 because it's a unit vector. And lo and behold, I have all three sides of this triangle. So I can calculate theta using the cosine law. So theta is equal to, so inverse cos of, so its opposite side is root 3, so root 3 squared minus 1 squared minus 1 squared, or negative 2 times 1 times 1. Okay. So let's calculate this here. So here we have cos inverse of root 3 squared is just going to be 3 minus 1 divided by negative 2 times 1 is just negative 2. And so we end up with 120 degrees. Okay, now this is where I have to be careful because I just realized now I shouldn't have used the angle theta because that's not what this represents. When I write this angle theta, it's representing the angle between them. So I really should have used a different variable here. Let me call that phi, because where is angle theta? Angle theta is this angle between the two vectors, okay? So of course we know the relationship between these vectors is that they're supplementary. So theta is equal to 180 minus 120, which is equal to 60 degrees. So this is negative 13, cos of 60 plus 1. Okay, and as we calculated before, this is just 1/2, so negative 13 over 2 plus 2 over 2 is negative 11 over 2. And there you have it, okay? So what we saw here was a couple of examples where we get to use these characteristics of the dot product. Again, distributivity, commutativity, associativity, and the definition, geometric definition of the dot product, but we had to do a little bit of work with this information that was given. Okay, so there'll be a couple of these in the assignment. All right, that's it for this part of the lesson.